98 million years ago, Giganotosaurus lived across what is now South America during the Late Cretaceous Period. It was one of the largest meat-eating dinosaurs ever discovered and may have been even longer than Tyrannosaurus rex. Its huge body, powerful jaws, and sharp teeth made it a skilled hunter in a land filled with giant, plant-eating dinosaurs. Before we begin our exploration into Giganotosaurus, we would appreciate if you could subscribe and comment below where in the world you're watching from and what the time is there. We always enjoy reading through your comments and connecting with our viewers. Giganotosaurus was one of the largest meat-eating dinosaurs that lived during the Late Cretaceous Period. It lived many millions of years before human beings appeared on Earth. Today it is known from fossil remains that were discovered in the southern part of South America. These fossils have helped scientists learn about its body, its way of life, and the environment where it lived. Although many details are still being studied, Giganotosaurus has become one of the best-known large dinosaurs because of its great size and the important fossil discoveries connected to it. The name Giganotosaurus has a special meaning. It comes from ancient Greek words that together mean giant southern lizard. The name was chosen because the fossils were found in the southern part of the world and because the animal was very large. Scientists often give dinosaurs names that describe something important about them, such as the place where they were discovered, the shape of their bodies, or a special feature that makes them different from other animals. In the case of Giganotosaurus, its name reflects both its great size and the region where it once lived. Giganotosaurus lived during the Late Cretaceous Period, about 98 million years ago. During this time, the Earth looked very different from the world people know today. The continents had already begun moving towards the positions they have now, but they were still changing. Large areas of land were covered by forests, open plains, rivers, lakes, and wetlands. The climate in many places was warmer than today, and many different kinds of reptiles, dinosaurs, birds, insects, fish, and plants lived across the land and in the water. The area where Giganotosaurus lived is now part of Argentina. During the time of the dinosaur, this region had many natural features that supported large animals. Rivers carried water across the land, helping plants grow in great numbers. Forests and open spaces gave plant-eating dinosaurs many places to find food. These large plant-eating animals became an important food source for large meat-eating dinosaurs. The land was full of life, and many different species shared the same environment. The discovery of Giganotosaurus was an important event in the study of dinosaurs. Fossils of this giant animal were found by a local fossil hunter named Ruben Dario Carolini. He found the bones in Patagonia, a region in southern Argentina. The discovery attracted the attention of scientists because the bones belonged to a very large meat-eating dinosaur that had never been described before. Careful study of the fossils showed that they represented a new species. Scientists officially described Giganotosaurus in the year 1995. The work was carried out by paleontologists Rodolfo Coria and Leonardo Salgado. They carefully examined the bones, measured them, studied their shapes, and compared them with the fossils of other known dinosaurs. After completing their research, they announced that the fossils belonged to a new dinosaur species, which they named Giganotosaurus carolini. The second part of the scientific name honored the fossil hunter who made the important discovery. The fossils of Giganotosaurus included parts of the skull, lower jaw, backbone, hips, legs, and other bones. Even though the skeleton was not complete, enough bones were preserved for scientists to understand much about the animal. Each fossil provided useful information. The skull helped scientists study the shape of the head and the arrangement of the teeth. The leg bones showed how the animal stood and walked. The backbone gave clues about the length and strength of the body. The skull of Giganotosaurus was very large. It contained many sharp teeth that were designed for cutting through the flesh of other animals. These teeth were replaced throughout the dinosaur's life. When one tooth was lost or damaged, another tooth slowly grew to take its place. This natural process helped the dinosaur keep strong and useful teeth throughout its lifetime. The teeth of Giganotosaurus were not all exactly the same. Some were slightly different in shape depending on where they were located in the jaws. The edges of the teeth had small sharp points that helped them cut into food. Scientists have studied these teeth carefully because they can reveal details about feeding habits. Fossil teeth also help researchers identify dinosaurs when complete skeletons are not available. The jaws of Giganotosaurus were built to open widely. Strong jaw muscles allowed the animal to bite into its food with force. The bones of the skull were connected in ways that supported powerful feeding. Every part of the head worked together during feeding, from the muscles and jaws to the teeth and neck. The structure of the skull shows that it was well suited for catching and eating large animals. The neck of Giganotosaurus supported the heavy skull. Strong neck muscles helped hold the head in position while the dinosaur walked, searched for food, and fed. The neck bones allowed movement in different directions, giving the animal flexibility while it explored its surroundings. A strong neck was an important part of its body because it had to support the weight of the large head every day. The body of Giganotosaurus was long and balanced. It moved on two powerful back legs while the front limbs were much smaller. These front limbs had 3 fingers with sharp claws. Although they were shorter than the back legs, they may still have been useful during feeding or while holding on to prey. Scientists continue to study their possible uses because soft body parts, such as muscles, are not preserved in the fossils. The back legs were among the strongest parts of the body. Thick bones supported the animal's weight and allowed it to move across different kinds of ground. The joints in the hips, knees, and ankles work together to produce steady movement. Fossil footprints from other large meat-eating dinosaurs help scientists understand how animals with similar bodies may have walked, even though no confirmed footprints of Giganotosaurus have been found. The feet of Giganotosaurus had large toes that spread its weight across the ground. Strong claws covered the ends of the toes. These claws helped provide grip while walking. The bones inside the feet were arranged in a way that supported the heavy body during movement. Every step required strength and balance because of the dinosaur's large size. The tail of Giganotosaurus was long and strong. It contained many connected bones that gave support to the body. The tail helped keep balance while the dinosaur moved. Large muscles attached to the tail also supported movement of the back legs. The tail was an important part of the body's overall structure and helped maintain stability during everyday activities. The skin of Giganotosaurus is not completely known because very little direct evidence has been found. No complete skin covering has been discovered with the main skeleton. Scientists study the skin impressions of related dinosaurs to learn what it may have looked like. Current evidence suggests that the body was likely covered with scales rather than feathers. Small scales may have covered different parts of the body, forming a protective outer layer. Like all dinosaurs, Giganotosaurus began its life by hatching from an egg. No confirmed eggs belonging to this species have been discovered, but scientists know that dinosaurs reproduced by laying eggs. The young animals probably looked similar to the adults in overall shape, although they were much smaller. As they grew, their bones became stronger and larger. Growth continued for many years before they reached full size. The bones of Giganotosaurus contain growth marks that can provide clues about age. Scientists examine very thin slices of fossil bones under powerful microscopes. These growth marks can help estimate how fast the dinosaur grew and how old it was when it died. This kind of research is called bone histology. It has become an important method for learning about the lives of extinct animals. Giganotosaurus belonged to a group of meat-eating dinosaurs known as carnivorous. Members of this group lived in different parts of the ancient world during the Cretaceous period. They shared several features, including large bodies, long skulls, and sharp cutting teeth. Over many years, scientists have discovered additional members of this group, helping build a better understanding of their evolution and distribution across ancient continents. The study of Giganotosaurus continues as new fossils are discovered and new scientific methods are developed. Modern technology allows researchers to create detailed digital models of fossil bones, examine their internal structure without causing damage, and test ideas about movement, growth, and feeding. Every new discovery adds more information to the growing picture of this remarkable dinosaur and helps scientists understand the ancient world in greater detail. Giganotosaurus lived during the Late Cretaceous Period, a time when dinosaurs were still the dominant land animals across much of the world. This part of Earth's history took place many millions of years before humans appeared. The Late Cretaceous lasted for a very long time, and during those years, many different kinds of dinosaurs, reptiles, birds, insects, fish and plants spread across different continents. Giganotosaurus lived during the later part of this period, around 98 million to about 96 million years ago. During that time, the world looked very different from the way it does today. The continents had already started moving away from each other after being joined together much earlier in Earth's history. Oceans were becoming wider, mountain ranges were slowly rising in different places, and new environments were forming across the land. The home of Giganotosaurus was in what is now the country of Argentina in South America. Today, Argentina is known for its wide grasslands, mountains, rivers, deserts, forests, and cold southern regions. During the time when Giganotosaurus lived, this land looked completely different. The climate, the plants, the animals, and the landscape all belong to a world that no longer exists. Instead of modern mammals, birds, and flowering plants becoming the most common forms of life, giant reptiles filled many parts of the land, while early birds, insects, small mammals, and other creatures lived alongside them. The fossils of Giganotosaurus were discovered in Patagonia, a large region that covers much of southern Argentina and parts of Chile. Patagonia is famous because many dinosaur fossils have been found there over many years. Rocks in this region have preserved the remains of animals that lived during different periods of Earth's history. Wind, rain, rivers, and natural changes slowly uncovered these ancient rocks, allowing scientists to discover bones that had remained buried for millions of years. The specific place where Giganotosaurus fossils were found belongs to an area known as the Carnivorous Formation. This formation is made up of layers of rock that formed during the Late Cretaceous Period. These rocks contain important clues about the environment that existed when Giganotosaurus was alive. Scientists study the rocks as carefully as they study the fossils, because the rocks help explain how the land looked, what kind of weather existed, where rivers flowed, and what kinds of plants and animals shared the same environment. The Carnivorous Formation is part of a larger group of rock layers called the Neuquén Group. These rock layers cover large parts of western Argentina. They formed over many millions of years as rivers carried sand, mud, and other materials across the land. They formed over many millions of years as rivers carried sand, mud, and other materials across the land. These materials slowly settled on the ground and later became solid rock. As animals died, some of their remains were buried by these natural deposits. Over long periods of time, the bones changed into fossils as minerals slowly replaced the original bone material. The land where Giganotosaurus lived was filled with wide river systems. These rivers carried fresh water across large areas and helped plants grow. The rivers also created floodplains where water spread during periods of heavy rainfall. These floodplains supported many different kinds of plants and animals. Trees, bushes, ferns, and other plants covered parts of the landscape, providing food for large plant-eating dinosaurs. Since many herbivorous dinosaurs gathered near these food sources, meat-eating dinosaurs such as Giganotosaurus also found plenty of hunting opportunities. The environment included sandy areas left behind by flowing rivers. River channels often changed direction over many years. As rivers shifted, they left behind new deposits of sand and mud. These changing river systems shaped the land and created different habitats where animals could live. Some places remained wet for long periods, while others became dry depending on rainfall and seasonal changes. Scientists believe the climate in this part of South America during the Late Cretaceous was generally warm. Temperatures stayed higher than those found in many places today. There were no ice sheets covering the poles like those seen during much later periods of Earth's history. Warm conditions allowed plants to grow across large areas for much of the year. These growing plants supported large populations of plant-eating dinosaurs, which in turn supported large predators. Rainfall probably changed during different seasons. Some parts of the year may have brought heavier rains that filled rivers and lakes. Other times were likely drier, causing water levels to fall. Animals living in this environment needed to survive both wet and dry conditions. Large rivers would have remained important sources of water throughout the year, attracting many kinds of animals. The forests where Giganotosaurus lived were not exactly like modern forests. Flowering plants had already begun spreading across the world, but many older plant groups were still very common. Tall conifer trees grew in many places. Ferns covered parts of the ground. Horsetails and other ancient plants thrived near rivers and wetlands. Cycads and other seed-producing plants also formed part of the landscape. These plants created different habitats where smaller animals could hide while larger animals searched for food. Flowering plants continued becoming more common during the Late Cretaceous. They produced flowers, seeds, and fruits that attracted insects and other animals. Although flowering plants had not yet completely replaced older plant groups, they were becoming an important part of the environment. Their spread slowly changed ecosystems across many regions of the world, including South America. The land supported enormous plant-eating dinosaurs. Among these were giant, long-necked sauropods that spent much of their time feeding on leaves from trees and other tall plants. Their large bodies required huge amounts of food every day. These animals moved across the landscape in search of fresh vegetation, leaving tracks and paths behind them. Their presence shaped the environment because they ate large amounts of plants and spread seeds through their movement. Some of the biggest animals living alongside Giganotosaurus belong to a group called Tyrannosaurs. These giant herbivores lived in many parts of South America during the Late Cretaceous. Their massive size made them difficult prey, although young, old, injured or weak individuals may have been more vulnerable to attacks from large predators. Other plant-eating dinosaurs also lived in the same region. Different species filled different roles within the ecosystem. Some fed close to the ground, while others reached higher branches. Their feeding habits reduced direct competition for food because each group focused on different kinds of plants or different heights of vegetation. Smaller meat-eating dinosaurs shared the environment with Giganotosaurus. These predators hunted animals much smaller than those targeted by giant hunters. Some chased fast prey across open ground, while others searched through forests and riverbanks for small reptiles, mammals, birds, or young dinosaurs. The presence of many different predators shows that the environment supported a rich supply of prey. Early mammals also lived in this ancient landscape. Most of them remained small and active during parts of the day or night when larger predators were less active. They fed on insects, seeds, fruits, and other small food sources. Although mammals had already appeared millions of years earlier, they remained much smaller than the dominant dinosaurs of the Late Cretaceous. Birds also lived during this period. Some had already developed features similar to modern birds, including feathers adapted for flight. They searched for insects, seeds, fish, or other small food items depending on the species. Their presence added more diversity to the ecosystem. Many reptiles, besides dinosaurs, lived in this environment. Lizards moved through vegetation. Crocodile relatives lived along rivers, lakes, and wetlands. Turtles spent time in fresh water, feeding on plants or small animals. Snakes had also begun spreading across different regions of the world during the Cretaceous period. Insects were extremely common. Beetles, dragonflies, flies, ants, termites, and many other insects filled different habitats. Some insects pollinated flowering plants, while others fed on leaves, wood, dead animals, or other insects. Their activities played an important role in maintaining healthy ecosystems. Fish lived in rivers and lakes throughout the region. Freshwater habitats supported different fish species that became food for crocodile relatives, birds, and other animals. Amphibians such as frogs also occupied wet environments where they fed on insects and other small creatures. The skies above Patagonia were occupied by flying reptiles known as pterosaurs. These animals had wings made from skin supported by an extended finger. Different species fed on fish, small animals, or other available food. They nested on cliffs, riverbanks, or open ground depending on the species. The landscape where Giganotosaurus lived probably included open woodlands mixed with thicker forests. River valleys contained richer plant growth because water remained available for longer periods. Higher ground may have supported different plant communities depending on soil conditions and rainfall. Natural events shaped the environment over time. Rivers flooded, changing their paths and leaving fresh layers of mud. Strong winds moved sand across open areas. Heavy rains sometimes caused erosion that exposed older rock layers before covering them again with new sediment. These natural processes helped bury animal remains, increasing the chances that fossils could form. Volcanic activity occurred in parts of South America during different times of the Cretaceous period. Volcanoes sometimes released ash, spartawas, that settled across large areas. Volcanic ash could quickly bury plants and animals, helping preserve remains under certain conditions. Ash also added minerals to the soil after long periods of weathering. The position of South America during the Late Cretaceous differed from its present location. The continent continued moving slowly because of the movement of Earth's tectonic plates. This movement happened over millions of years. Oceans gradually widened between South America and Africa after both continents separated from the earlier southern supercontinent known as Gondwana. The separation of continents affected weather patterns, ocean currents, and the spread of animals and plants. As land connections disappeared, species living on one continent often evolved separately from those living elsewhere. This helped create unique groups of dinosaurs in South America. Giganotosaurus belonged to one of these uniquely South American groups of giant, meat-eating dinosaurs. During the Late Cretaceous, South America contained several large predators that differed from those living in North America, Europe, Asia, or Africa. Long periods of isolation allowed these dinosaur groups to develop their own features over time. Scientists use fossils from many different locations within Patagonia to rebuild the ancient environment. Fossilized leaves show which plants grew there. Fossil pollen reveals changes in vegetation over time. Fossil wood preserves details about ancient forests. Footprints show where animals walked, while fossil eggs provide information about nesting behavior for some dinosaur species. The rocks containing Giganotosaurus fossils include sandstone and mudstone. Sandstone formed where rivers carried sand and deposited it in channels or floodplains. Mudstone formed when very fine particles settled in calmer water. These different rock types help scientists understand changing conditions across the landscape. The fossil remains found in the Candelejos Formation include more than dinosaur bones. Scientists have also discovered fossil plants, turtles, crocodile relatives, fish, insects, and many other ancient organisms. Every fossil provides another piece of information about the world where Giganotosaurus lived. The ancient rivers supported rich ecosystems. Plants growing along riverbanks created shelter for many animals. Fallen trees formed natural hiding places. Pools left behind after floods became homes for fish, amphibians, insects, and small reptiles. These habitats supported life throughout the year. The soil in floodplain areas probably contained nutrients brought by rivers during seasonal floods. These nutrients helped plants grow well after floodwaters returned to normal levels. Healthy plant growth supported large populations of herbivorous dinosaurs, allowing predators to find food regularly. Scientists believe that some parts of Patagonia experienced periods of drought. During dry times, rivers became even more important because animals gathered near remaining water sources. Such gatherings increased interactions between predators and prey. Waterholes may have become busy places filled with different kinds of animals seeking water each day. The weather likely changed from season to season, even though temperatures remained generally warm. Seasonal rainfall affected plant growth, river levels, and animal movement. Dinosaurs probably adjusted their behavior according to these natural changes. Fossil evidence suggests that forests did not completely cover the region. Instead, many open spaces existed between wooded areas. Open ground allowed large dinosaurs to move across long distances while searching for food, mates, or nesting places. Open areas also made it easier for large predators to spot potential prey. The landscape probably contained gentle hills as well as flat floodplains. Rivers cut through these areas, creating valleys where water collected. Small streams joined larger rivers before flowing across the countryside. Wetlands formed in low areas where water remained for long periods. Ground cover included ferns, low shrubs, young trees, and many other plants. This vegetation provided shelter for insects, small reptiles, mammals, and young dinosaurs. Larger animals often walked through these areas while feeding or traveling. Many kinds of dinosaur eggs have been discovered in Argentina. These discoveries suggest that different dinosaur species returned to suitable nesting areas during breeding seasons. Some may have chosen sandy riverbanks, while others preferred higher ground, less likely to flood. The presence of nesting sites shows that Patagonia provided suitable conditions for raising young dinosaurs. Warm temperatures, available food, and enough space supported growing populations over many generations. Scientists continue discovering new fossils throughout Patagonia. Each discovery adds more knowledge about the environment where Giganotosaurus lived. Sometimes even small fossil fragments reveal important details about ancient climates, plant life, or animal behavior. The fossil record also shows that many different dinosaur species lived at different times within the same general region. Rock layers formed over millions of years, meaning that animals preserved in different layers did not always live together. Scientists carefully study the exact rock layer where each fossil is found to determine its age and relationship to other fossils. Dating these rock layers involves studying volcanic minerals and other geological evidence. By measuring changes within certain minerals over long periods, scientists estimate when the rocks formed. These methods indicate that Giganotosaurus lived during the earlier part of the Late Cretaceous, around 98 million to about 96 million years ago. The world during this time contained higher sea levels than many later periods. Large inland seas covered parts of some continents. Coastlines differed greatly from those seen today. Although Giganotosaurus lived inland, changes in global sea levels affected climates and weather patterns across many regions. South America supported many unique ecosystems because of differences in rainfall, elevation, rivers, and soil. Giganotosaurus occupied one part of this diverse continent. Other regions contained different dinosaur communities adapted to local conditions. The ancient environment remained active with daily life. Herbivores searched constantly for fresh plants. Predators looked for food, birds flew between trees. Insects pollinated flowers and fed on leaves. Crocodile relatives rested near water before hunting fish or other animals. Mammals searched for insects and seeds beneath vegetation. Every group depended on the surrounding environment for survival. Plant growth changed throughout the year according to rainfall and temperature. Fresh leaves appeared during growing seasons, providing abundant food for herbivores. Dead plants returned nutrients to the soil after breaking down. Insects, fungi, and tiny organisms helped recycle plant material within the ecosystem. Floods occasionally buried forests beneath layers of mud and sand. Fallen trees sometimes became fossilized after being covered quickly by sediment. These fossil forests provide valuable evidence about the types of trees that grew in Patagonia during the Late Cretaceous. Strong sunlight reached much of the landscape because Earth's climate remained warm. Plants used this sunlight to grow, supporting the food chain that sustained both herbivores and predators. Large dinosaurs needed enormous amounts of energy, making healthy plant communities essential for the survival of the ecosystem. The rivers flowing across Patagonia slowly changed direction over thousands of years. Old channels filled with sediment, while new channels formed elsewhere. Animals living in these areas adapted to the changing landscape as water sources shifted across the floodplains. Many fossil sites contain bones from several animals buried together. Some may have died during floods, droughts, or other natural events. Others became buried gradually after death. Scientists carefully examine the position of each fossil to understand how burial occurred. Wind also played a role in shaping the environment. Dry periods allowed wind to move sand across open ground, forming sandy areas between river systems. Plants growing in these places had to survive periods with less water. The ancient ecosystem where Giganotosaurus lived supported a wide variety of living things because different habitats existed close together. Rivers, forests, open plains, wetlands, sandy ground, and wooded areas all provided homes for different species. This diversity helped maintain stable populations of plants and animals over long periods. Although millions of years have passed since Giganotosaurus walked across Patagonia, the rocks beneath the ground still preserve evidence of its world. Fossil bones, fossil plants, footprints, ancient river deposits, volcanic ash layers, pollen grains, and mineral changes continue helping scientists understand where this giant predator lived and the natural environment that surrounded it during every stage of its life. The ancient environment of the late Cretaceous was very different from the world that exists today. This part of Earth's history took place during the final stage of the Cretaceous period, which lasted from about 100 million years ago until about 66 million years ago. The late Cretaceous began around 100 million years ago and continued until the great extinction event that ended the age of the non-flying dinosaurs around 66 million years ago. During this long stretch of time, the planet was filled with many kinds of living things. Dinosaurs lived on every major landmass, while the seas were home to many large reptiles, fish, shellfish, and tiny organisms. Forests, rivers, lakes, wetlands, coastal plains, deserts, and mountain regions provided homes for countless plants and animals. Every part of the environment worked together to support life in many different ways. The continents during the late Cretaceous were not in the same positions that they are today. The giant landmass that had existed much earlier had already broken apart into smaller continents. These continents slowly continued moving across the surface of the Earth. Their movement changed the shape of coastlines, created new oceans, raised mountains, and opened new pathways for animals and plants to spread into different places. Even though the continents looked different, many areas already resembled parts of the modern world. North America, South America, Africa, Europe, Asia, Australia, and Antarctica all existed, although they were located in different positions and were separated by different seas. Many shallow seas covered parts of the continents during this time. One of the largest inland seas stretched across the middle of North America. This great body of water divided the land into two large sections for millions of years. Warm, shallow water covered huge areas where fish, sharks, shellfish, marine reptiles, and many other sea animals lived. The seafloor collected layers of mud, sand, shells, and the remains of tiny sea creatures. Over a very long time, these layers became rock. Today, these rocks preserve many fossils that help scientists understand the ancient environment. The climate during the late Cretaceous was generally warm across much of the world. Average temperatures remained higher than those of many later periods. There were no large sheets of permanent ice covering the poles. Because there was little or no polar ice, sea levels remained much higher than they are today. Large amounts of ocean water spread over low-lying land, creating wide coastal plains and shallow inland seas. These conditions provided many different habitats where plants and animals could grow and reproduce. The warm climate affected rainfall patterns across the world. Some regions received heavy rain throughout much of the year. Thick forests covered these wet places with many kinds of trees, shrubs, vines, ferns, and flowering plants. Rivers carried fresh water through these forests, supporting many animals that depended on reliable water sources. Other areas experienced long dry seasons with less rainfall. These regions supported plants that could survive with limited water. The variety of wet and dry environments allowed many different species to live across the continents. The atmosphere during the late Cretaceous also played an important role in shaping the environment. Carbon dioxide levels were higher than they are today, Carbon dioxide is a gas that helps trap heat in the atmosphere. Higher amounts of this gas helped keep global temperatures warm. Warm oceans released moisture into the air, leading to clouds and rainfall in many places. Winds carried moisture across continents, helping forests and wetlands develop in suitable regions. The oceans were rich with life during the Late Cretaceous. Tiny floating organisms filled the surface waters. These microscopic forms of life became the base of many food chains. Small fish fed on them, while larger fish hunted the smaller ones. Marine reptiles hunted fish, squid, and other sea animals. Sharks also lived in many oceans and fed on a wide range of prey. Shellfish lived on the sea floor, while corals built reefs in warm, shallow water. Sea lilies, sea stars, sea urchins, and many other invertebrates lived in these underwater habitats. The sea floor contained many different environments. Soft, muddy bottoms supported worms, shellfish, and burrowing animals. Rocky areas allowed other creatures to attach themselves firmly to hard surfaces. Coral reefs created homes for many different species living close together. These reefs protected young animals, provided food, and supported rich communities of marine life. Different ocean depths also supported different kinds of animals, depending on light, temperature, pressure, and available food. Rivers played an important role in shaping the land. Water flowing from mountains and hills carried sand, mud, and small rocks into lower areas. These materials settled along riverbanks and floodplains. Floods spread fresh layers of soil across wide areas, helping many plants grow. Rivers also created lakes, marshes, and wetlands where many animals found food, water, and shelter. Fossils found in ancient river deposits show that dinosaurs often lived close to these freshwater environments. Floodplains were among the richest habitats during the Late Cretaceous. Seasonal flooding renewed the soil and supported thick plant growth. Large plant-eating dinosaurs gathered in these areas because food was plentiful. Meat-eating dinosaurs followed them, searching for hunting opportunities. Smaller reptiles, amphibians, mammals, insects, turtles, and birds also lived within these productive environments. Fallen trees, ponds, and patches of dense vegetation created many different places where animals could hide, feed, or build nests. Wetlands covered large areas in many regions. Marshes, swamps, and shallow ponds supported rich plant life. Tall plants grew along the edges of standing water. Fish swam through channels while turtles rested along muddy banks. Crocodile relatives hunted in the water, waiting for fish or animals that came to drink. Frogs and salamanders reproduced in shallow pools. Insects laid eggs in the water, providing food for fish, birds, and other small animals. Forests during the Late Cretaceous contained many different kinds of trees. Earlier plant groups such as conifers still covered large areas. Cycads and ginkgo trees also continued growing in many places. At the same time, flowering plants became increasingly common. These plants spread across forests, riverbanks, wetlands, and open fields. They produced flowers, fruits, and seeds that supported many insects, birds, and small mammals. The spread of flowering plants changed many ecosystems by creating new food sources and new habitats. Flowering plants became one of the most important parts of the Late Cretaceous environment. They developed many different forms suited to different climates and soils. Some grew into large trees while others remained as shrubs or small ground plants. Their flowers attracted insects that carried pollen between plants. This process helped many flowering species reproduce successfully. Fruits protected seeds and encouraged animals to spread them into new areas after eating them. Insects became even more important as flowering plants expanded. Bees, wasps, flies, butterflies, beetles, ants, and many other insects visited flowers in search of food. While feeding, they carried pollen from one flower to another. Many insects also fed on leaves, wood, fruits, or dead plant material. Others hunted smaller insects. Insects themselves became food for birds, reptiles, amphibians, mammals, and many other animals. Their activities helped recycle nutrients throughout the environment. Ferns continued growing in many regions despite the spread of flowering plants. Ferns thrived in moist forests, along streams, and in shaded areas beneath larger trees. They reproduced using spores rather than seeds. Thick carpets of ferns often covered the forest floor. Young dinosaurs and many smaller animals could move through these dense plants while searching for food or hiding from predators. Conifer forests remained widespread across much of the world. These evergreen trees produced cones instead of flowers. Many species tolerated cooler or drier conditions than some flowering plants. Their tall trunks supported branches filled with needle-like leaves. Birds nested among the branches while insects lived beneath the bark. Fallen needles formed thick layers on the forest floor, affecting the types of smaller plants that could grow underneath. Open woodland areas existed between dense forests and wide grass-free plains. True grass had not yet spread across the world, as it would much later. Instead, open areas contained low shrubs, ferns, flowering plants, and scattered trees. Large plant-eating dinosaurs often moved through these landscapes searching for fresh vegetation. Different plant species grew during different seasons, creating changing food supplies throughout the year. Mountain ranges influenced weather and habitats during the Late Cretaceous. As continents moved, collisions between landmasses pushed parts of the Earth's crust upward. Mountains affected rainfall by changing wind patterns. Rivers began high in these mountains before flowing toward lower land. Cooler temperatures existed at higher elevations, allowing different plant communities to develop. Animals living in mountainous areas adapted to steeper land and changing weather conditions. Volcanic activity also shaped the environment in some regions. Volcanoes released lava, ash, gases, and other materials onto the land and into the atmosphere. Fresh volcanic rock slowly broke down into fertile soil that supported new plant growth. Ash sometimes buried forests and animals, preserving remains that later became fossils. Volcanic activity could also temporarily affect local weather by releasing large amounts of dust and gases into the air. Earthquakes sometimes accompanied the movement of continents and volcanic activity. Shifting rocks beneath the ground changed the landscape over long periods. Rivers altered their paths, lakes formed, and valleys developed. These changes created new habitats while destroying others. Plants and animals constantly adjusted to these changing conditions over many generations. The Late Cretaceous environment supported many different kinds of dinosaurs. Large plant eaters fed on leaves, branches, seeds, fruits, and other plant material. Some used broad beaks to clip vegetation, while others stripped leaves from branches with their teeth. Their feeding changed the appearance of forests and open woodlands by removing large amounts of plant growth. Seeds passed through their digestive systems and were spread across the landscape. Large meat-eating dinosaurs hunted other animals within these environments. They searched forests, floodplains, river valleys, and open land for prey. Some probably hunted alone, while others may have hunted with members of their own species in certain situations. Smaller predators hunted mammals, reptiles, birds, amphibians, insects, and young dinosaurs. Every level of the food chain depended on the health of the surrounding environment. Small dinosaurs lived beside the giant species. Many of these smaller animals ran quickly through forests and open ground. Some climbed over fallen logs, while others nested close to rivers or among thick plants. Their smaller size allowed them to feed on insects, seeds, fruits, leaves, and other food sources that larger dinosaurs often ignored. This helped many different dinosaur species live within the same region. Birds continued developing during the Late Cretaceous. Some already looked quite similar to modern birds, while others still kept many dinosaur features. Feathers helped them fly, stay warm, attract mates, and protect eggs. Birds nested in trees, on cliffs, near rivers, and on the ground. Many fed on insects, fish, seeds, or small animals. Their ability to fly allowed them to move easily between different habitats. Early mammals also shared the environment with dinosaurs. Most mammals remained small and were active during times when large predators were less likely to hunt. They fed on insects, seeds, fruits, eggs, and small animals. Some climbed trees while others lived underground or among thick vegetation. Their ability to survive in many different habitats helped them remain successful throughout the Late Cretaceous. Reptiles other than dinosaurs were common across the landscape. Crocodile relatives lived in rivers, lakes, and wetlands. Turtles occupied freshwater habitats and coastal waters. Lizards hunted insects and other small animals. Snakes also existed during this period and occupied different environments depending on their feeding habits. These reptiles formed important parts of local ecosystems. Amphibians remained closely connected to water. Frogs, salamanders, and similar animals depended on moist habitats for reproduction. They lived around ponds, streams, marshes, and wetlands where eggs could develop safely. Amphibians fed on insects and other small animals, while becoming prey for birds, reptiles, mammals, and fish. Freshwater fish filled rivers and lakes throughout the Late Cretaceous world. Many species fed on insects, smaller fish, plants, or tiny water organisms. Larger fish hunted smaller ones. Seasonal flooding sometimes connected rivers with lakes and wetlands, allowing fish to spread into new areas. Fish also served as food for crocodiles, birds, marine reptiles entering freshwater, and some dinosaurs that hunted near water. Marine reptiles ruled many ocean habitats. Long-necked species searched for fish and squid in open water. Other marine reptiles had powerful jaws suited for catching larger prey. Their streamlined bodies helped them move efficiently through the sea. They gave birth in the water rather than returning to land. These reptiles occupied many parts of the oceans and formed an important part of marine ecosystems. Sharks were already diverse during the Late Cretaceous. Different species occupied shallow coastal waters, deep oceans, and open seas. Some hunted fish while others fed on shellfish or scavenged dead animals. Their sharp senses helped them locate food over long distances. Sharks played an important role in keeping marine ecosystems balanced by removing weak or injured animals. Tiny ocean organisms greatly influenced the environment despite their small size. Many floated freely in surface waters where sunlight supported their growth. Others lived near the sea floor. When these tiny organisms died, many settled onto the ocean bottom. Over long periods, their remains formed thick deposits that later became limestone and chalk in many parts of the world. The coastline constantly changed as sea levels rose and fell over very long periods. Coastal plains expanded during times of higher sea levels and shrank when water retreated. Beaches, lagoons, tidal flats, and estuaries formed where rivers met the sea. These areas supported many fish, shellfish, birds, reptiles, insects, and plants. Coastal environments often contained rich supplies of food because freshwater and saltwater mixed together. Storms affected many parts of the Late Cretaceous world. Heavy rain sometimes caused rivers to overflow their banks. Strong winds damaged forests and scattered branches across the landscape. Coastal storms reshaped beaches and carried sand inland. Lightning sometimes started fires in dry forests, clearing old vegetation and allowing new plants to grow later. Wildfires occurred naturally in some dry environments. Dead plants and dry leaves provided fuel when lightning struck. Fires removed old vegetation and returned nutrients to the soil through ash. Some plants recovered quickly after fire, while others required longer periods to return. Animals escaped into rivers, burrows, or nearby unburned habitats until conditions improved. Seasonal changes continued throughout the year, despite the generally warm climate. Some regions experienced wetter seasons, followed by drier periods. Plants responded by producing new leaves, flowers, fruits, and seed at different times. Animals adjusted their feeding, nesting, breeding, and movement according to changing weather and food availability. These yearly cycles shaped the lives of nearly every species. The length of daylight changed with the seasons depending on location. Areas closer to the poles experienced larger seasonal differences in daylight than regions near the equator. Even without permanent ice sheets, polar regions still experienced cooler temperatures than tropical regions. Forests grew even in some high-latitude areas because the climate remained much warmer than in later Ice Age periods. The soils of the Late Cretaceous varied greatly from one place to another. River valleys contained rich soils built from repeated flooding. Volcanic regions developed fertile soils after fresh rock weathered. Sandy soils formed near ancient coastlines and deserts. Different plants adapted to different soil types, creating many distinct habitats across the continents. Desert regions also existed during the Late Cretaceous. These dry areas received little rainfall and supported plants able to survive long periods without much water. Reptiles, insects, and certain dinosaurs adapted to these conditions by conserving water and remaining active during cooler parts of the day. Wind shaped sand into dunes while occasional streams briefly flowed after heavy rain. The process of fossil formation began within these environments whenever plants or animals died under suitable conditions. Many remains quickly disappeared because they were eaten or broken down by living organisms. Others became buried beneath mud, sand, volcanic ash, or river sediments before complete decay could occur. Minerals slowly replaced or filled parts of bones, shells, wood, and leaves over very long periods. These preserved remains provide valuable information about the late Cretaceous environment today. Scientists study fossil pollen, fossil wood, fossil leaves, and fossil seeds to understand ancient plant life. Different plant species produced unique pollen grains that often survived for millions of years. By examining these tiny fossils under microscopes, researchers learn which plants grew in different regions and how climates changed through time. Fossil footprints also reveal important details about the late Cretaceous environment. Tracks preserved in soft mud show where dinosaurs walked, ran, rested, or gathered in groups. Some trackways indicate movement along riverbanks or across flood plains. Others show animals crossing shallow water or muddy ground after rain. These footprints help scientists understand behavior as well as ancient landscapes. Ancient burrows preserved in rocks show where small animals lived beneath the ground. Burrowing protected animals from predators, extreme temperatures, and dry conditions. Fossil nests containing eggs reveal where some dinosaurs and birds reproduced. In some rare cases, embryos remained preserved inside eggs, providing valuable information about development before hatching. The chemical makeup of ancient rocks also provides clues about the late Cretaceous environment. Minerals preserved within rocks help scientists estimate past temperatures, rainfall, and ocean conditions. Layers of sediment show repeated flooding, changing sea levels, volcanic eruptions, and long periods of calm environmental conditions. Ocean currents moved warm water around the world during the late Cretaceous. These currents influenced climate by carrying heat from tropical regions toward higher latitudes. Warm oceans supported many marine species and helped maintain relatively mild conditions across much of the planet. Changes in ocean circulation affected rainfall, temperatures, and the distribution of sea life. The movement of nutrients through ecosystems supported healthy plant and animal populations. Dead plants and animals broke down through the work of bacteria, fungi, insects, and other small organisms. Nutrients returned to the soil and water, where they became available for new plant growth. Plant eaters consumed vegetation, while predators fed on other animals. Waste products also returned nutrients to the environment, continuing this natural cycle. Fungi quietly played an important role in forests and other habitats. They broke down fallen wood, dead leaves, and animal remains. This process released nutrients back into the soil, where plant roots absorbed them. Some fungi formed close relationships with plant roots, helping plants gather water and minerals from the soil more effectively. Bacteria were present in every environment during the late Cretaceous. They lived in soil, water, plants, animals, and decaying material. Many bacteria helped decompose dead organisms, while others supported healthy soils by participating in nutrient cycles. Although invisible without special equipment, these tiny living things remained essential to the functioning of ancient ecosystems. Life during the late Cretaceous depended on constant interactions between the land, the atmosphere, freshwater systems, and the oceans. Climate influenced plant growth, plants supported animals, animals spread seeds, rivers carried nutrients, oceans affected weather, and geological activity reshaped landscapes over long periods. Every environment contained countless living organisms connected through feeding, reproduction, movement, growth, and the continuous changes taking place across the ancient world. Giganotosaurus was one of the largest meat-eating dinosaurs that ever lived on Earth. It belonged to a group of dinosaurs known as theropods. These dinosaurs walked on two strong legs, had powerful jaws, sharp teeth, and large claws. Giganotosaurus lived during the late Cretaceous period in what is now South America. Even though scientists continue to study new fossils and learn more about this animal, the remains already discovered provide a clear picture of its size, body shape, and many physical features. Every bone that has been found helps researchers understand how this giant dinosaur lived, moved, hunted, and survived in its ancient environment. The size of Giganotosaurus has attracted attention ever since its fossils were first discovered. Scientists carefully study every preserved bone to estimate the total length, height, and body weight of the animal. Because no complete skeleton has been found, these estimates are based on the fossil bones that are available and on careful scientific measurements. Even with some missing parts, researchers agree that Giganotosaurus reached an enormous size during its lifetime. Most scientific studies suggest that an adult Giganotosaurus reached a body length of about 40 to 43 feet from the tip of its snout to the end of its tail. This made it one of the biggest land predators known from the fossil record. Its body stretched over a very long distance, allowing space for a large skull, a long neck, a deep chest, strong hips, muscular legs, and an extended tail. Every part of the body worked together to support such a huge animal during daily life. The height of Giganotosaurus also reflected its massive body. At the hips, an adult stood around 13 feet tall. When the neck and head were raised, the top of the animal reached much higher. The long legs lifted the body well above the ground, giving it a clear view of the surrounding land. This height also helped support the heavy body while allowing the dinosaur to move across wide open areas. Body weight is one of the hardest features for scientists to estimate because muscles, skin, fat, and other soft tissues are rarely preserved in fossils. Researchers study the thickness and strength of the bones to estimate how much weight the skeleton carried. Most studies suggest that an adult Giganotosaurus weighed between 8 and 10 tons. These estimates may change slightly as new discoveries are made, but they show that this dinosaur had a very heavy body, supported by strong bones and powerful muscles. The skull of Giganotosaurus was one of its most noticeable features. It measured close to 6 feet in length. The skull was long and deep, providing space for powerful jaw muscles. The bones of the skull were connected in ways that allowed strength while keeping the head from becoming too heavy. Openings within the skull reduced the total weight of the head without reducing its strength. This helped the dinosaur carry such a large skull more comfortably while moving and feeding. The front of the skull ended in a long snout. The nose area contained openings that allowed air to pass into the breathing system. The shape of the snout may also have helped the animal detect smells carried by the wind. A strong sense of smell would have been useful when searching for food or recognizing other members of its own species. The eyes of Giganotosaurus were placed on the sides of the skull, although they still faced somewhat forward. This arrangement gave the dinosaur a broad view of the area around it. The large eye sockets suggest that the eyes themselves were also large. Good eyesight would have helped the dinosaur notice movement over long distances and remain aware of changes in its surroundings. Above the eyes were raised ridges made of bone. These ridges gave the skull a rough and powerful appearance. Scientists think these structures may have protected the eyes from direct blows or from branches and other objects in the environment. They may also have played a role in helping members of the species recognize one another. The jaws of Giganotosaurus were extremely strong. Large jaw muscles attached to the back of the skull and allowed the animal to open and close its mouth with great force. The lower jaw was long and deep, providing room for muscles and supporting many large teeth. Strong joints connected the upper and lower jaws, allowing repeated biting during feeding. The teeth of Giganotosaurus were shaped for cutting flesh. Each tooth was long, narrow, and slightly curved backward. Small, sharp edges along the front and back of each tooth increased their ability to slice through meat. These edges worked much like tiny cutting points that helped separate flesh from bone. The teeth were not designed for chewing food into small pieces. Instead, the dinosaur bit into flesh, tore away large sections, and swallowed them. Many teeth measured several inches in length. New teeth formed beneath older ones throughout the dinosaur's life. When a tooth broke or fell out, another tooth slowly moved into its place. This natural replacement system allowed Giganotosaurus to continue feeding even after losing teeth during hunting or eating. The neck of Giganotosaurus was thick and muscular. It contained many connected bones called vertebrae. Strong muscles attached to these bones and supported the heavy head. The neck allowed the dinosaur to move its head in different directions while watching its surroundings or feeding. Flexible joints between the neck bones provided movement while still keeping the neck strong enough to carry the large skull. The body of Giganotosaurus was deep and wide through the chest. The ribs curved around the lungs, heart, and other internal organs. The large chest provided room for organs that supplied oxygen and blood throughout the enormous body. Strong muscles also attached to the ribs and backbone, helping support movement and breathing. The backbone extended from the skull to the end of the tail, each vertebra connected with the next, forming a strong but flexible support for the body. The vertebrae increased in size through different parts of the body depending on the amount of weight they carried. Thick ligaments and muscles attached to the backbone, giving strength during walking, running, and feeding. The shoulders of Giganotosaurus supported relatively small front limbs. These arms were much shorter than the hind legs but still contained strong bones and muscles. Each arm ended in a hand with 3 fingers. Each finger carried a curved claw made of bone covered by a hard outer layer during life. The claws may have helped the dinosaur hold prey close to its body or assist during feeding. Although the arms were short, they were not weak. Muscle attachment areas on the arm bones show that they could produce considerable strength. The shoulder joint allowed controlled movement, although the arms probably could not reach very far forward. Scientists continue to study how these limbs were used during hunting and feeding. The chest connected to a strong hip region that supported much of the dinosaur's weight. The hip bones were broad and firmly joined to the backbone. This area formed the main support for the hind legs. Every step taken by Giganotosaurus placed great pressure on these bones, so they needed to be thick and strong. The hind legs were the largest limbs on the body. Each leg contained a large thigh bone connected to the hip. Below the thigh bone were the lower leg bones that extended towards the ankle. Thick muscles surrounded these bones and produced the force needed for walking, running, standing, and turning. The knee joints allowed the legs to bend smoothly during movement. Strong ligaments held the joints together while reducing unnecessary movement. The lower legs ended in large feet with 3 main weight-bearing toes. Each toe ended with a curved claw. These claws were useful for gripping the ground while walking or running. The feet of Giganotosaurus spread its heavy body weight across the ground. Thick pads beneath the feet likely absorbed part of the force created with every step. This helped reduce stress on the bones and joints. The wide shape of the feet also improved balance while moving over different types of land. The tail of Giganotosaurus formed a large part of its total body length. It contained many connected vertebrae, supported by muscles and tendons. The tail helped balance the heavy front part of the body. As the dinosaur walked or changed direction, the tail shifted to maintain stability. Large muscles at the base of the tail also helped move the hind legs by attaching to the upper leg bones. The skin of Giganotosaurus is not fully known because complete skin impressions have not been found together with its skeleton. Scientists study skin impressions from closely related dinosaurs to make careful estimates. The body was most likely covered with scales of different sizes. Some scales may have been small and closely packed, while others were larger in certain areas. These scales protected the skin from injury and helped reduce water loss. The color of Giganotosaurus remains unknown because fossil bones do not preserve the original body colors in most cases. Scientists cannot say with certainty whether it was green, brown, gray, or another color. Different color patterns may have existed among individuals depending on age, sex, or the environment where they lived. At present, these ideas remain possibilities rather than confirmed facts. Muscles covered much of the skeleton and gave Giganotosaurus its powerful appearance. Large muscles surrounded the neck, shoulders, chest, hips, thighs, and tail. Muscle attachment marks preserved on fossil bones allow scientists to estimate the size and position of many muscles. These muscles produced the force needed for movement, hunting, feeding, and supporting the heavy body throughout its daily activities. The breathing system of Giganotosaurus was probably highly efficient. Like many other theropod dinosaurs, it likely had air sacs connected with the lungs. These air sacs helped move air through the breathing system and may also have reduced the total weight of parts of the skeleton. Some bones contained hollow spaces connected with these air sacs, making the body lighter while maintaining strength. The heart of such a large animal needed to pump blood through the entire body, including the long neck and large head. Although soft organs are not preserved as fossils, scientists estimate that the heart was large and powerful enough to supply oxygen and nutrients to every part of the body. The blood vessels also had to withstand the pressure needed to move blood over such long distances within the body. The digestive system occupied much of the body cavity. After swallowing large pieces of meat, the stomach and intestines processed the food and absorbed nutrients needed for growth, repair, and energy. Because meat is rich in nutrients, Giganotosaurus may not have needed to eat every day, although the exact feeding pattern remains uncertain. When people talk about the largest meat-eating dinosaurs that ever lived, one question appears again and again. Was Giganotosaurus bigger than Tyrannosaurus rex? This question has been discussed by scientists, dinosaur fans, museum visitors, and writers for many years. The answer is not as simple as saying that one animal was larger in every way. Scientists study fossils to learn about the size of these animals, but fossils are often incomplete. New discoveries can also change earlier ideas. Because of this, the answer depends on which part of the body is being studied and which fossil specimen is being measured. Giganotosaurus was a giant meat-eating dinosaur that lived during the Late Cretaceous Period in what is now Argentina in South America. Tyrannosaurus rex lived much later in what is now the western part of North America. These two dinosaurs did not live at the same time, so they never met in nature. Even though they lived in different places and at different times, people often wonder which one was the bigger animal because both were among the largest meat-eating dinosaurs ever discovered. The first fossils of Giganotosaurus were found in Argentina during the early part of the 1990s. The discovery attracted great attention because the bones belonged to a dinosaur that appeared to be larger than many other known meat-eating dinosaurs. Scientists carefully cleaned the fossils, studied the bones, and described the new dinosaur. They gave it the name Giganotosaurus carolini. Since then, more research has been carried out to understand its body, its way of life, and its place among other large predators. Tyrannosaurus rex had already been known to science for many years before Giganotosaurus was discovered. Fossils of Tyrannosaurus rex had been found in North America and had become famous around the world. Museums displayed huge skeletons, books described its powerful body, and many people came to know it as one of the greatest predators in Earth's history. When Giganotosaurus was announced, people immediately wanted to know if this newly discovered dinosaur was actually bigger than the well-known Tyrannosaurus rex. One of the main ways scientists estimate the size of a dinosaur is by measuring the length of its fossil bones. The skull, leg bones, backbone, hips, and tail all provide useful information. When a skeleton is complete, it becomes easier to estimate the full body length. Unfortunately, complete dinosaur skeletons are very rare. Many fossils are missing important parts because the animal died in a place where not every bone was preserved. Some bones may also have been destroyed before they could be discovered. This means that scientists often have to estimate the missing parts by studying related dinosaurs with similar body shapes. The known fossils of Giganotosaurus suggest that it reached a body length of around 40 feet or slightly more. Some estimates place it at about 43 feet. different studies have suggested slightly different lengths, because they use different methods to estimate the missing bones. Scientists understand that these estimates are not exact. They continue to improve them whenever better fossils become available. The body length of Tyrannosaurus rex has also been estimated many times. Many large adults reached about 40 feet in length. Some of the biggest known individuals may have grown slightly longer. Like Giganotosaurus, the exact length depends on which fossil specimen is being studied and how missing bones are reconstructed. The largest known Tyrannosaurus rex fossils show that it was an enormous animal with a very long body, a large skull, and a heavy tail that helped balance its movement. When people only look at body length, Giganotosaurus appears to have been slightly longer than many Tyrannosaurus rex individuals. This is one reason why some people say that Giganotosaurus was bigger. A longer body does make an animal appear larger. However, body length is only one part of overall size. Scientists also study body weight, height, bone strength, and body shape because these features help show how large an animal truly was. Estimating the weight of an extinct dinosaur is much more difficult than measuring its length. Flesh, muscles, skin, and internal organs are not usually preserved. Scientists must estimate how much muscle covered the bones and how thick different parts of the body were. Modern computer models have helped improve these estimates, but different studies still produce different results. Many studies suggest that Giganotosaurus weighed somewhere between about 8 and 9 metric tons. Some estimates are slightly higher, while others are slightly lower. These numbers are based on the known skeleton and computer models that estimate the amount of muscle and other soft tissue covering the bones. The weight of Tyrannosaurus rex has also been studied using many different methods. Some of the largest known adults are estimated to have weighed between about 8 and 10 metric tons. A few studies have suggested even greater weights for the largest individuals. These estimates continue to change as new research becomes available. Because of these estimates, many scientists believe that although Giganotosaurus may have had a slightly longer body, Tyrannosaurus rex may have been heavier. A heavier body means more mass packed into the skeleton. This suggests that Tyrannosaurus rex had a deeper chest, thicker muscles and stronger bones that supported a greater amount of weight. The skull of Giganotosaurus was very long. It measured close to 6 feet in length. The skull was narrow from side to side and had many openings that helped reduce its overall weight. This lighter design allowed the head to remain large without becoming too heavy for the neck. Its jaws held many sharp teeth that were shaped for slicing through the flesh of prey. The skull of Tyrannosaurus rex was built differently. It was wider, deeper, and much stronger. Although it was not always longer than the skull of Giganotosaurus, it was much thicker and stronger. The bones of the skull were firmly connected, allowing the animal to produce one of the strongest bites known among land animals. The shape of the skull reflects the different way Tyrannosaurus rex hunted and fed. The teeth of Giganotosaurus were long, narrow, and sharp. They were designed to cut into flesh and leave deep wounds. The edges of the teeth had tiny saw-like markings that helped them slice through meat. Some teeth could grow several inches long, although only part of each tooth was visible outside the jaw, because the roots remained inside the bone. Tyrannosaurus rex had thicker teeth with strong roots. These teeth could handle enormous pressure when the jaws closed. The teeth were less likely to break under heavy force. Scientists believe this helped Tyrannosaurus rex bite through flesh and bone while feeding. The neck of Giganotosaurus was powerful enough to support its long head. Strong muscles attached to the neck bones allowed it to move the skull while attacking prey. The neck was built for quick movement as well as strength. Large muscles connected the head to the shoulders and upper back. The neck of Tyrannosaurus rex was even more heavily built. Thick neck bones supported the large skull and the great force produced during biting. Strong muscles helped keep the head stable while feeding. This heavy neck added to the total body mass of the animal. The chest of Giganotosaurus was deep enough to contain large lungs, a strong heart, and other important organs. Like other large dinosaurs, it needed an effective breathing system to support its active lifestyle. Large lungs helped supply oxygen to the muscles during movement. The chest of Tyrannosaurus rex appears to have been even deeper and wider. This wider body added more volume to the animal and increased its estimated weight. The ribs curved around the body to protect the organs and support the muscles attached to the shoulders and backbone. The hips of Giganotosaurus were broad and supported powerful hind legs. These hips connected the backbone to the legs through strong joints that carried the weight of the animal. The hip bones also provided attachment points for large muscles, used during walking and running. The hips of Tyrannosaurus rex were also massive. Thick hip bones carried the heavy body and allowed the dinosaur to remain stable while moving. The large muscles attached to the hips produced the force needed to move such a heavy animal across the landscape. The leg bones of Giganotosaurus were long and strong. The thigh bone and lower leg bones supported the body during movement. The long legs suggest that the dinosaur could travel across large areas while searching for food. Strong joints helped reduce stress during walking. The leg bones of Tyrannosaurus rex were even thicker. Their greater width suggests they carried a heavier body. Scientists study the strength of fossil bones because stronger bones usually indicate that they supported greater weight. The thick legs of Tyrannosaurus rex fit well with the idea that it may have been heavier than Giganotosaurus, even if it was not quite as long. The tail of Giganotosaurus formed a large part of its total body length. Long tail bones stretched behind the hips and balanced the heavy front part of the body. Powerful muscles connected the tail to the legs, helping produce force during movement. The tail of Tyrannosaurus rex also played an important role in balance and movement. Like other large theropod dinosaurs, the tail helped keep the body stable while walking and turning. Strong muscles attached near the base of the tail and extended into the legs, helping the animal move its heavy body efficiently. The skull of Giganotosaurus was one of the most important parts of its body, because it contained the brain, the eyes, the nose, the jaws, and the teeth that allowed this giant meat-eating dinosaur to survive in the ancient world. Scientists have spent many years studying the skull bones that were found with the fossil remains of this dinosaur. Every piece of bone provides valuable information about how Giganotosaurus lived, how it found food, how it captured prey, and how it used its powerful jaws. Even though the fossil skeleton is not completely complete, the preserved skull bones have given researchers a detailed understanding of the shape, size, and structure of the head. Careful study of these fossils has helped scientists rebuild the skull and understand how the different bones fitted together. Giganotosaurus lived during the Late Cretaceous Period, about 98 million years ago, in what is now Argentina. During that time, the land was home to many large animals, including giant, plant-eating dinosaurs that could provide enough food for a very large predator. To hunt and feed successfully, Giganotosaurus needed a skull that was strong enough to support powerful muscles while remaining light enough to move quickly. The design of its skull shows that nature shaped it for this purpose over many millions of years. The skull of Giganotosaurus measured about 1.5 meters in length, making it one of the largest dinosaur skulls ever discovered. Its great length allowed room for many large teeth and powerful jaw muscles. The front of the skull was long and narrow instead of short and deep. This shape helped the animal open its mouth widely and place many teeth into the body of its prey during a bite. The long shape also provided space for the nasal bones and the large openings that reduced the overall weight of the skull. Like many large meat-eating dinosaurs, the skull was not made from one single piece of bone. Instead, it was built from many separate bones that were joined together. Each bone had a special position and purpose. The upper jaw bones held the upper teeth, while the lower jaw supported the lower teeth. Other bones protected the brain, supported the eyes, and formed the nose. The bones were connected firmly, creating a strong framework that could withstand the forces produced during feeding. One interesting feature of the skull was the presence of many openings called fenestrae. These openings reduced the weight of the skull without making it too weak. A lighter skull allowed Giganotosaurus to move its head more easily while hunting. The openings also created space for muscles, blood vessels, and other soft tissues that were necessary for normal body functions. Reducing unnecessary weight helped the dinosaur carry such a large head without placing too much strain on the neck. The upper surface of the skull was rough in several places. These rough areas probably supported skin, scales, or other soft tissues that covered the bones during life. Scientists believe the head was covered with thick skin instead of feathers. The skin may have contained small scales similar to those found in other large dinosaurs. Some areas may also have supported thicker coverings that protected the skull during feeding or fights with members of the same species. The eye sockets of Giganotosaurus were large and faced mostly toward the sides of the head, although they also allowed some forward vision. The large eyes would have helped the dinosaur see movement across wide areas of land. Good eyesight was important for locating prey from a distance. Large eyes also gathered more light, allowing better vision during cloudy weather or near sunrise and sunset when light levels were lower. The bones around the eyes formed strong protective rings that helped keep the eyes safe from injury. While attacking struggling prey, branches, dust, or moving body parts could easily strike the face. Thick bones around the eyes reduced the risk of serious damage. Protecting the eyes was important because vision played a major role in hunting and avoiding danger. The nose of Giganotosaurus contained large openings that allowed air to pass into the breathing passages. Inside the skull were spaces connected to the nasal cavity. These spaces may have helped improve breathing efficiency and reduce skull weight. Scientists continue studying these features to understand exactly how air moved through the head. Modern scanning technology has revealed details that cannot be seen from the outside alone. The brain of Giganotosaurus occupied only a small portion of the skull. Like many dinosaurs, the brain was much smaller than the total size of the head. Even though the brain was not very large, it controlled all the body's activities, including movement, balance, sight, smell, hearing, and feeding. Fossil evidence suggests that the parts of the brain connected with smell were well developed. A strong sense of smell would have helped Giganotosaurus detect prey, locate animal remains, and recognize scents left by other dinosaurs. The inner ear played an important role in balance and head movement. Scientists have studied the spaces inside the skull, where the inner ear was located. These studies suggest that Giganotosaurus could hold its head in a stable position while walking or running. Good balance allowed smooth movement even with such a large skull. Stable head position also helped keep the eyes focused on moving prey. the neck muscles attached firmly to the back of the skull. Large attachment areas show that these muscles were powerful. Strong neck muscles allowed the dinosaur to lift, lower, and swing its heavy head. During feeding, these muscles probably helped pull flesh from prey after the teeth had entered the body. The neck muscles worked together with the jaw muscles to produce effective feeding movements. The lower jaw consisted of several bones joined together. The largest bone was the dentary, which held many of the lower teeth. Other bones strengthened the jaw and supported muscles and joints. The joint connecting the lower jaw to the skull allowed the mouth to open very wide. This wide opening made it easier to bite into large animals. The jaw joint had to withstand enormous forces during feeding. Fossil evidence shows that the bones around the joint were thick and well supported. This strength reduced the chance of injury while biting struggling prey. Even though the bite was powerful, the joint also needed enough flexibility for repeated opening and closing during feeding. The teeth of Giganotosaurus were among its most important hunting tools. Unlike human teeth, dinosaur teeth were constantly replaced throughout life. When one tooth broke or fell out, another tooth slowly grew beneath it. This replacement system ensured that the dinosaur always had sharp teeth available. Hunting large animals often damaged teeth, so constant replacement was necessary for survival. Each tooth had a curved shape that pointed backward toward the throat. This curve helped keep prey from escaping once bitten. As the jaws closed, the curved teeth entered flesh easily and held firmly. If prey struggled to pull away, the backward curve made it more difficult to escape. The teeth were long, narrow, and sharply pointed. Their shape was well suited for cutting through skin, muscles, and other soft tissues. The sharp tips entered flesh quickly, while the edges sliced as the jaws moved. This cutting action allowed Giganotosaurus to remove large pieces of meat from animal bodies. The edges of the teeth contain tiny, saw-like ridges known as serrations. Although these ridges were very small, they greatly improved cutting ability. Under magnification, the serrations appear as rows of tiny points running along both edges of each tooth. These tiny structures acted like the edge of a cutting blade, helping the teeth slice through flesh more effectively. Scientists have examined fossil teeth under powerful microscopes to study these serrations. They have found that each serration had a shape that reduced stress while cutting. The design helped prevent cracks from spreading through the tooth. This made the teeth stronger and less likely to break during feeding. The enamel covering each tooth formed a hard outer layer that protected the softer material inside. Enamel is one of the hardest substances produced by vertebrate animals. Thick enamel allowed the teeth to survive repeated contact with flesh, tendons, and occasionally bone. Even so, broken teeth are found in fossil collections, showing that damage sometimes occurred despite their strength. The roots of the teeth extended deep into the jawbones. Deep roots gave the teeth a secure hold during biting. When the jaws closed with force, the teeth remained firmly in place instead of becoming loose. Strong attachment was necessary because large prey could struggle violently during attacks. Different teeth occupied different positions within the jaws. Teeth near the front helped grip prey, while teeth farther back continued cutting as the jaws closed. Together they formed an effective cutting system along the entire length of the mouth. The arrangement ensured that many teeth contacted prey during each bite. The spaces between neighboring teeth allowed room for replacement teeth developing below the surface. As old teeth wore down or broke, new teeth slowly moved upward into position. Scientists have discovered replacement teeth inside fossil jawbones through detailed scanning. These hidden teeth reveal that several generations of teeth could exist within the jaw at the same time. Wear marks found on fossil teeth provide important information about feeding habits. Some teeth show polished areas where repeated contact occurred. Others contain tiny scratches produced while cutting meat. Occasionally, damaged tips reveal that hard objects such as bone were contacted during feeding. Careful examination of these marks helps scientists understand how Giganotosaurus used its teeth throughout its life. The bite of Giganotosaurus has been studied using fossil evidence, computer models, and knowledge gained from living reptiles and birds. Researchers have built digital models of the skull to estimate the forces produced by the jaws. These studies suggest that the bite was strong enough to capture and feed on very large animals. Instead of depending only on crushing force, the shape of the skull and teeth indicates that cutting played an important role during feeding. The jaw muscles attach to large areas on the skull, behind the eyes, and along the upper parts of the head. When these muscles contracted, they pulled the lower jaw upward, closing the mouth. Larger muscles generally produced stronger bites, and the skull shows extensive areas where these muscles were anchored. Muscles are not preserved in fossils, but the rough attachment marks left on bones allow scientists to estimate their size. By studying these marks, researchers can reconstruct the likely arrangement of muscles. Computer models then estimate how these muscles functioned while opening and closing the jaws. The skull balanced strength with reduced weight. Thick, supporting bones were placed where stress was greatest, while large openings removed unnecessary mass from other areas. This design allowed the dinosaur to move its head more efficiently while still maintaining enough strength for feeding. When Giganotosaurus attacked prey, it likely opened its jaws widely before bringing the teeth into the body. Once the teeth entered flesh, the powerful neck muscles could pull backward, increasing the cutting effect of the serrated teeth. This movement would have produced deep wounds that caused heavy bleeding and serious injury. The large number of teeth increased the chance that several teeth entered the prey at the same time. Multiple cutting points spread the force across a wider area while creating many wounds. If one tooth broke during feeding, many others continued working. Scientists continue discovering new information whenever additional fossils are found or new technology becomes available. High-resolution scanning allows researchers to examine the inside of fossil skulls without damaging them. Digital reconstruction helps replace missing pieces and correct damage caused during fossilization. These methods provide a clearer picture of the skull, teeth, and bite of Giganotosaurus, and continue to expand scientific understanding of this remarkable prehistoric predator. The arrangement of the bones inside the skull also helped protect important nerves and blood vessels that supplied the eyes, jaws, nose, and other parts of the head. Small openings in the fossil bones show where these nerves and blood vessels passed. Scientists study these openings carefully because they provide information about how the living animal sensed its surroundings and how different parts of the head received oxygen and nutrients. The pattern of these openings also helps researchers identify individual skull bones when only broken pieces of fossils are available. The roof of the mouth contained hard, bony surfaces that supported the upper jaw. These bones helped keep the skull stable while the animal was feeding. As the jaws closed around prey, pressure traveled through many connected bones instead of remaining in only one area. This spread of force reduced the chance that a single bone would fail during repeated feeding. The connected structure allowed the skull to remain firm while still containing spaces that kept the head from becoming unnecessarily heavy. The bones forming the cheeks created broad surfaces where large jaw muscles could pass. Although these muscles disappeared long before the fossils formed, the shape of the surrounding bones provides clear evidence that they occupied a great deal of space inside the skull. Thick muscles allowed the jaws to close with speed and strength. During feeding, these muscles worked repeatedly as the dinosaur tore away pieces of flesh and repositioned its jaws for another bite. The front part of the snout contained many small openings that allowed nerves to reach the skin covering the face. These nerves probably made the snout sensitive to touch. A sensitive snout could help the dinosaur detect the position of prey during close contact. It may also have allowed Giganotosaurus to recognize objects placed directly in front of its mouth, even when they were difficult to see. Scientists have also examined the texture of the fossil bones on the front of the skull. Some areas show fine grooves and tiny pits that indicate where blood vessels once lay beneath the skin. These blood vessels supplied oxygen and nutrients to the tissues covering the face. Healthy skin was important because it protected the skull from injury, infection, and damage while feeding. The nostrils were positioned near the front of the snout. Air entered through these openings before passing into the nasal passages inside the skull. The lining of these passages contained tissues that warmed and cleaned the air before it reached the lungs. Although these soft tissues are no longer present, the shape of the bones allows scientists to estimate their location and size. The sense of smell was probably one of the most useful senses available to Giganotosaurus. Fossil studies suggest that the nerves connected with smell were well developed. A strong sense of smell would have allowed the animal to notice the scent of injured animals from long distances. It may also have helped locate the remains of animals that had already died. Smell could also play a role in recognizing members of the same species, identifying possible mates, and detecting the presence of rivals. The teeth nearest the front of the mouth were slightly different in shape from those positioned farther back. Front teeth were especially useful for making the first contact with prey. After these teeth entered the body, the remaining teeth followed as the jaws closed further. This sequence allowed the bite to spread across a large section of flesh rather than concentrating on only a few teeth. Each tooth grew within its own socket in the jawbone. The sockets surrounded the roots closely, providing strong support. Soft tissues held the teeth firmly inside these sockets while still allowing old teeth to fall out naturally when replacement teeth were ready. Fossil jawbones sometimes preserve both an old tooth and a developing replacement tooth within the same socket, giving scientists direct evidence of this replacement process. The replacement of teeth continued throughout the animal's life. Young Giganotosaurus individuals replaced smaller teeth while adults replaced much larger ones. The growth of replacement teeth required a steady supply of minerals from the body. Calcium and phosphorus played important roles in forming strong enamel and healthy tooth structure. The dinosaur obtained these minerals through the food it ate, and its body directed them toward developing teeth whenever replacements were needed. Microscopic examination of fossil teeth has revealed tiny growth lines inside the tooth material. These lines formed as the teeth developed over time. By counting and measuring them, scientists can estimate how long it took for a new tooth to form. This work has shown that tooth replacement was a continuous process, rather than something that happened only after major injury. Some fossil teeth contain cracks that formed while the dinosaur was still alive. In several cases, these cracks show signs of healing or wear, indicating that damaged teeth remained useful for some time before eventually being replaced. This demonstrates that Giganotosaurus did not need perfectly undamaged teeth to continue feeding successfully. Even worn or chipped teeth could still cut through flesh until new teeth took their place. Scientists have also discovered isolated Giganotosaurus teeth away from skeletons. These loose teeth probably fell out naturally during feeding or after replacement. Such discoveries are valuable because teeth are often preserved better than many other bones. Their strong enamel allows them to survive long after softer bones have broken apart. Finding these isolated teeth helps researchers identify places where Giganotosaurus once lived, even if no complete skeleton is present. The shape of the lower jaw indicates that it could withstand repeated stress from opening and closing many times during a meal. Feeding on a large animal would not have been completed with a single bite. Instead, the jaws would have continued working for an extended period as the dinosaur removed flesh piece by piece. The bones show features that supported this repeated movement without becoming unstable. The muscles responsible for opening the jaws were also important. While much attention is given to the muscles that closed the jaws, the muscles that lowered the lower jaw allowed the mouth to open quickly before another bite. These muscles work together with the neck muscles to position the head properly during feeding. Researchers use computer simulations to study how force traveled through the skull during biting. These digital models show that pressure spread across several major bones instead of remaining only in the jaws. Such studies help explain why certain bones were thicker, while others contained large openings. The pattern of force distribution reflects the demands placed on the skull during everyday feeding. The skull also had to protect the brain from sudden movements. When a large predator bit into struggling prey, the head could experience rapid motion. Strong bones surrounding the brain reduced the risk of injury from these movements. The brain case formed a secure chamber that enclosed the brain while allowing nerves to leave through carefully placed openings. Inside the skull, passages carried nerves from the brain to the eyes, ears, nose, and jaws. These nerves transmitted information that allowed the dinosaur to react quickly to changes in its surroundings. If prey moved suddenly or attempted to escape, the nervous system coordinated the muscles needed to adjust the position of the head and jaws. The hearing ability of Giganotosaurus remains an area of active scientific study. Fossil evidence from the inner ear suggests that it could detect sounds useful for survival. Hearing may have helped locate moving animals, recognize calls from other dinosaurs, or become aware of approaching danger. The exact range of sounds it detected cannot be known with certainty, but the preserved structures provide useful clues. The bite itself was not simply a matter of muscle strength. Successful feeding depended on the combined action of the skull bones, jaw joints, muscles, teeth, neck, and nervous system. Every part had to function together. If any one of these parts was seriously injured, hunting and feeding would become much more difficult. The pressure created during a bite was concentrated mainly at the sharp edges of the teeth. Because the contact area was small, the teeth could enter flesh efficiently. Once inside, the serrated edges continued cutting as the jaws moved. This action created wounds that extended deeper with each movement of the head and neck. Some fossil teeth display rounded tips caused by long periods of use. Even after becoming less sharp, these teeth continued functioning until replacement occurred. This gradual wearing process shows that the teeth remained useful throughout much of their lifespan. Continuous replacement ensured that the overall cutting ability of the jaws remained effective despite normal wear. Young Giganotosaurus individuals probably had proportionally smaller skulls and shorter teeth than fully grown adults. As they matured vivical, the skull expanded, the jaw muscles became larger, and the teeth increased in size. This gradual growth allowed young animals to feed on prey suited to their changing body size, while developing the powerful feeding structures seen in adulthood. Growth of the skull did not occur evenly in every direction. Different bones expanded at different rates, while maintaining proper alignment with neighboring bones. This controlled growth ensured that the jaws continued fitting together correctly throughout the animal's life. Proper alignment was essential because poorly matched teeth would reduce feeding efficiency and increase the risk of injury to the jaws. Fossil discoveries from different individuals show slight variations in skull shape. Some of these differences may reflect age, while others may represent normal variation among individuals. Small differences in bone thickness, tooth spacing, or surface texture are expected within any animal population. Scientists carefully examine these variations before deciding whether they represent different growth stages or individual characteristics. Hunting behavior and feeding habits are among the most interesting parts of learning about Giganotosaurus, because they help scientists understand how this giant, meat-eating dinosaur survived in the ancient world. Even though no human ever saw a living Giganotosaurus, scientists can study its fossil bones, teeth, skull, legs, feet, and the rocks where its fossils were found. They can also examine marks left on fossil bones, ancient footprints, and the remains of other animals that lived in the same place. All of this information allows researchers to build a detailed picture of how this large predator may have searched for food, caught prey, fed on meat, and stayed alive in its natural environment. Giganotosaurus lived during the Late Cretaceous Period in what is now part of Argentina. At that time, the land contained wide open areas, forests, rivers, lakes, and floodplains. Many different kinds of animals shared this environment. There were giant plant-eating dinosaurs, smaller dinosaurs, early birds, crocodile relatives, turtles, fish, insects, and many other living things. This rich environment gave Giganotosaurus many opportunities to find food throughout its life. As a large meat-eating dinosaur, Giganotosaurus needed a great amount of food to support its body. Large animals use a great deal of energy simply by moving, growing, and carrying their weight. A predator of this size could not survive by catching only tiny animals. It needed prey that provided enough meat to meet its daily needs. Scientists believe that much of its hunting was probably directed toward medium-sized and large plant-eating dinosaurs that lived in the same region. The shape of the skull gives many clues about feeding behavior. The skull of Giganotosaurus was long and deep. This design allowed large jaw muscles to attach firmly inside the skull. Strong muscles helped the jaws close with enough force to grip struggling prey. The skull also held many sharp teeth that were shaped for cutting through flesh. Instead of crushing bones into small pieces, these teeth were better suited for slicing meat from the body of another animal. Each tooth had small edges that acted like tiny cutting points. These edges helped the teeth pass through skin, muscle, and other soft tissues. When the jaws closed, the teeth from the upper and lower jaws worked together to make deep cuts. If a tooth became damaged or fell out during feeding, another tooth slowly grew to replace it. This continuous replacement was very important because hunting large animals placed great stress on the teeth. Scientists think that Giganotosaurus may have attacked prey by delivering repeated bites. Instead of holding on to an animal for a long time, it may have bitten, pulled away, and bitten again. Every bite could leave deep wounds that caused heavy bleeding and serious injury. A wounded animal would gradually become weaker, making it easier for the predator to continue its attack. The neck of Giganotosaurus also played an important role during feeding. Strong neck muscles helped support the heavy head while hunting and eating. These muscles allowed the animal to pull pieces of meat from a carcass with powerful movements. The neck also helped control the head during quick biting actions when chasing prey. The body structure of Giganotosaurus suggests that it was an active hunter. Its long legs indicate that it could move at a steady speed across open ground. Although it was extremely large, its legs were built for movement rather than standing still all the time. Good movement would have helped it travel across its territory while searching for animals to hunt. Its tail also supported hunting activities. The long tail acted as a balancing structure while the animal walked, turned, or changed direction. Good balance helped the predator remain stable during movement and while attacking prey. Stable movement reduced the chance of falling during a chase or while feeding on uneven ground. Good eyesight may have been another important part of hunting. The position of the eyes suggests that Giganotosaurus could judge distance well enough to strike at moving prey. Clear vision would have helped it notice movement across open landscapes and identify possible targets from a distance. Sharp eyesight would also have helped it avoid danger and move safely through its environment. The sense of smell was probably also useful. Many meat-eating animals depend on smell to locate food. Giganotosaurus may have used its nose to detect the scent of injured animals or dead bodies from far away. A strong sense of smell could guide it toward easy meals without the need to hunt every time it became hungry. Hearing may also have contributed to survival. Sounds made by large plant-eating dinosaurs, young animals calling to adults, or groups moving through forests and floodplains could have helped Giganotosaurus locate prey. Hearing would also allow it to notice other predators or possible threats nearby. Scientists continue to discuss whether Giganotosaurus hunted alone or in groups. Fossils cannot give a complete answer. Some researchers think that a large predator could hunt by itself because of its great size and powerful body. A single adult would already be a dangerous hunter, capable of attacking many kinds of prey. Other researchers believe that at least sometimes several Giganotosaurus individuals may have lived or hunted near one another. If several adults or young adults worked together, they might have been able to control very large prey more easily. Working together could reduce the effort needed from each individual and increase the chance of success when attacking giant plant-eating dinosaurs. There is no direct proof showing exactly how often group hunting happened. Fossil evidence rarely preserves behavior. Most ideas about hunting in groups come from the discovery of fossils found close together, or from studies of living animals that hunt cooperatively. Because behavior does not become fossilized, scientists remain careful when discussing this possibility. Young Giganotosaurus probably had feeding habits that differed from those of fully grown adults. Newly hatched young were much smaller and weaker. They could not attack huge prey immediately after hatching. Instead, they likely fed on insects, small reptiles, small mammals, young dinosaurs, or animals that could be caught without great danger. As young Giganotosaurus grew larger, their hunting skills probably improved through experience. Practice would have helped them learn how to move quietly, judge distance, choose suitable prey, and avoid injury. Young animals that learned successful hunting methods had a better chance of reaching adulthood. Adult Giganotosaurus probably selected prey carefully. Attacking a healthy giant animal carried serious risks. Large plant-eating dinosaurs often had strong legs, powerful tails, thick bodies, and great size. Some also possessed natural defenses that could seriously injure a predator. A broken bone or severe wound could make hunting much more difficult and reduce the animal's chance of survival. Because of these dangers, Giganotosaurus may have searched for animals that were injured, sick, old, separated from a group, or very young. Such animals were usually easier to overpower than healthy adults. Choosing weaker prey would reduce the chance of injury during an attack while still providing a large amount of food. The hunting process probably began with searching rather than chasing. Giganotosaurus likely spent much of its day moving through its territory while watching, smelling, and listening for signs of prey. This steady search may have covered large areas because food was not always available in one location. Once prey was located, the predator probably moved closer before attacking. Remaining unnoticed for as long as possible would improve the chance of success. Vegetation, changes in the land and natural features along rivers and floodplains may have helped hide its approach until it was close enough to strike. When the attack began, speed over a short distance was probably more important than long-distance running. A sudden burst of movement could close the remaining gap between predator and prey. Quick bites aimed at soft parts of the body would increase the chances of causing serious injury early in the attack. Large prey often struggled after being bitten. Giganotosaurus may have followed an injured animal until it became too weak to continue. Heavy blood loss, damaged muscles, and exhaustion would gradually reduce the prey's ability to escape. This method would lower the need for long physical struggles that might injure the predator. Feeding began once the prey was no longer able to resist. The sharp teeth sliced through skin before reaching muscles and internal organs. Large pieces of meat were probably swallowed without much chewing. Like many meat-eating reptiles today, Giganotosaurus likely relied on strong stomach acids to help break down food after swallowing it. After opening the body, Giganotosaurus probably fed on the soft organs first because they were easy to reach and required less effort to remove. These organs contained large amounts of nutrients and moisture. Eating these parts early also made it easier to reach the deeper muscles inside the body. As feeding continued, the dinosaur likely removed large strips of muscle from the neck, shoulders, hips, and legs. These muscles provided a great amount of meat that could support the predator. For a long time, the jaws worked with repeated closing and pulling movements while feeding. Each bite cut through flesh, and the powerful neck helped pull meat away from the body. Since the teeth were designed for slicing instead of grinding, the food was probably swallowed in large chunks. The stomach then carried out most of the work of breaking down the meat during digestion. Scientists believed that the digestive system of Giganotosaurus was well suited for processing animal tissue. Strong stomach acids would have helped dissolve muscles, fat, skin, and other soft parts. Bones may have been swallowed in small amounts by accident while feeding, but there is little evidence that this dinosaur regularly crushed and consumed large quantities of bone. Smaller bone pieces that entered the stomach could have been softened by digestive acids before passing through the body. Water was another important part of daily life. Like every land animal, Giganotosaurus needed water to survive. Rivers, lakes, ponds, and streams that crossed its habitat would have provided regular drinking places. These water sources also attracted many plant-eating animals. As a result, areas near water may have offered good opportunities for hunting because prey visited them often. The changing seasons may have influenced hunting activities. During wetter times, plants grew more successfully, supporting large numbers of plant-eating dinosaurs. During drier periods, animals may have gathered closer to permanent water sources. Such gatherings could increase the chances of finding prey. Giganotosaurus probably adjusted its movements as the environment changed throughout the year. The size of its hunting territory was likely quite large. A giant predator needed enough space to locate food on a regular basis. If prey became scarce in one area, it probably traveled farther in search of better hunting grounds. Fossil evidence shows that the ancient landscape included many connected habitats, allowing large animals to move over long distances. Energy management was an important part of survival. Hunting required strength, and unsuccessful attacks used valuable energy. For this reason, Giganotosaurus probably avoided unnecessary movement whenever possible. It may have rested after eating a large meal, allowing its body to digest food before becoming active again. Large meals could provide enough energy to reduce the need for immediate hunting. Feeding opportunities did not always depend on successful hunting. Dead animals that had already died from disease, injury, old age, flooding, or other natural causes could also serve as food. Scientists believe that many large meat-eating dinosaurs probably fed on carcasses whenever they found them. This behavior allowed them to gain food without the risks involved in attacking living prey. A carcass may also have attracted several meat-eating animals at the same time. If another predator arrived while Giganotosaurus was feeding, conflict could occur. Because Giganotosaurus was among the largest predators in its environment, its size alone may have discouraged many smaller meat-eaters from approaching too closely. Still, disputes over food were likely a natural part of life whenever several animals reached the same carcass. Large bodies usually needed large amounts of protein and fat to remain healthy. Fresh meat supplied these nutrients. Muscle tissue provided protein that supported body growth and the repair of damaged muscles. Fat stored inside prey animals supplied energy that could help sustain the predator between successful hunts. Internal organs also contained important nutrients that supported normal body functions. The growth of Giganotosaurus depended on regular feeding during its younger years. Juveniles likely needed frequent meals because they were still developing. As bones lengthened and muscles became larger, a steady supply of nutrients was necessary. Individuals that found enough food would have grown faster and become stronger hunters as they approached adulthood. Periods of food shortage were probably unavoidable. Natural disasters, disease among prey animals, changing weather, or movement of herds into different regions could reduce the amount of available food. During these times, Giganotosaurus may have traveled farther, accepted smaller prey, or relied more heavily on scavenging to survive until hunting conditions improved. Injuries also affected hunting success. A damaged leg, injured foot, broken tooth, or wound from prey could reduce the ability to chase and capture animals. Fossil bones of many dinosaurs show signs of healed injuries, proving that some individuals survived serious accidents. A recovering Giganotosaurus may have depended more on slower prey or carcasses while its body healed. The replacement of teeth was especially valuable because feeding placed constant pressure on the mouth. Sharp teeth sometimes cracked when biting into tough tissue or striking bone. As older teeth wore down, new teeth slowly developed beneath them. Eventually, the older teeth fell out and were replaced by fresh ones, allowing the animal to continue feeding effectively throughout its life. The arms of Giganotosaurus were much smaller than its legs, but still contained muscles and claws. Scientists continue to study exactly how these arms were used during feeding. They may have helped hold the body steady while the jaws removed meat, or assisted in limited ways during close contact with prey. Their main role in hunting remains uncertain, because the skull and jaws clearly performed most of the work. The feet also contributed to successful hunting. Strong feet supported the animal's great weight while moving across different types of ground. The toes ended in large claws that helped provide grip on soil, mud, and rocky surfaces. Good footing reduced the chance of slipping during an attack or while feeding beside rivers and uneven ground. Weather conditions probably influenced hunting behavior from day to day. Rain could soften the ground, leaving tracks that revealed the recent movement of prey animals. Dry conditions might make travel easier in some places, but reduce water availability. Wind could carry scents over long distances, helping the predator detect animals or carcasses that could not yet be seen. Different ages of prey may have required different hunting methods. Young plant-eating dinosaurs were smaller and easier to overpower, although they were often protected by adults. Adult prey offered much more meat, but also presented greater danger. Choosing which animal to attack required careful judgment based on opportunity and risk. Some fossil sites contain bite marks on dinosaur bones that match the size and shape of large meat-eating dinosaur teeth. These marks provide important evidence about feeding behavior. They show that predators bit deeply into flesh, and sometimes left marks on bones while removing meat. Although it is not always possible to identify the exact species that made each bite mark, such discoveries support the idea that large predators actively fed on large dinosaur carcasses. Scientists also study broken and healed bones in plant-eating dinosaurs. Some injuries may have resulted from failed attacks by predators. An animal that escaped with bite wounds could survive if the injuries healed over time. Fossils showing healed damage reveal that not every hunting attempt ended with a successful capture. The digestive process likely continued for many hours after a large meal. During this time, Giganotosaurus may have reduced its activity while nutrients were absorbed into the body. Digestion required energy, and resting after feeding would allow the body to process the large amount of meat more efficiently. Once digestion was complete and hunger returned, the search for food would begin again. The sense of timing was probably important during hunting. Plant-eating dinosaurs moved through the landscape while searching for food and water. Giganotosaurus may have learned the places where prey appeared most often. Returning to these areas regularly could increase the chance of finding animals without wandering aimlessly across the landscape. Very large prey could provide enough food for an extended period. If the carcass remained undisturbed, Giganotosaurus might return to feed more than once before the meat spoiled completely, or was consumed by other meat-eating animals and scavengers. Weather, insects, and bacteria would gradually break down the remaining flesh, limiting how long the carcass could serve as a food source. Young Giganotosaurus probably became more skilled with each successful hunt. Experience would improve their ability to recognize safe opportunities, judge the behavior of prey, and use their strength more effectively. Learning through repeated hunting attempts was likely an important part of reaching full adulthood in the challenging environment of the late Cretaceous. Scientists continue to examine newly discovered fossils because each discovery adds more information about the feeding habits of Giganotosaurus. Every tooth, jawbone, footprint, bite mark, and fossilized skeleton helps build a clearer understanding of how this giant predator searched for food, captured prey, fed on large animals, survived periods of scarcity, and adapted its hunting behavior to the changing conditions of its ancient world. Growth, reproduction, and the life cycle were very important parts of the daily existence of Giganotosaurus. Every living creature begins life, grows over time, reaches adulthood, reproduces, and eventually dies. Although no person was present to watch Giganotosaurus. During its lifetime, scientists have learned many details by studying fossils, fossil bones, footprints, nesting areas of related dinosaurs, and the bones of young and adult dinosaurs. Each new discovery helps researchers understand how this giant, meat-eating dinosaur developed from a tiny animal inside an egg into one of the largest land predators that ever lived. Like all dinosaurs, Giganotosaurus started its life inside an egg. The adult female would have produced eggs after mating with a male during the breeding season. Scientists do not know the exact time of year when Giganotosaurus reproduced, because the changing seasons during the Late Cretaceous period were different from those in many places today. The weather, food supply, rainfall, and the condition of the land probably affected the best time for laying eggs. The female would have needed enough food and energy to produce healthy eggs because forming eggs required a great deal of nutrients from her body. The eggs of Giganotosaurus have never been found with complete certainty. Even though many dinosaur eggs have been discovered around the world, it is often difficult to identify which species laid a particular egg. The eggs of large meat-eating dinosaurs were likely strong enough to protect the developing young while still allowing air to pass through tiny openings in the shell. These tiny openings helped the growing baby receive oxygen while it remained inside the egg. Without enough oxygen, the developing young could not survive until hatching. Inside each egg, a small embryo slowly formed over time. At first, the embryo was extremely tiny, but it continued to grow as it received nutrients from the yolk inside the egg. The yolk contained fats, proteins, vitamins, minerals, and other nutrients needed for healthy development. The embryo also formed bones, muscles, organs, skin, eyes, and teeth before hatching. During this stage, the young Giganotosaurus remained protected inside the shell, while its body slowly became strong enough for life outside the egg. The developing embryo changed little by little each day. Tiny bones became longer and stronger. The skull took shape and the jaws slowly formed with developing teeth inside them. The legs and arms became more complete as muscles attached to the bones. The heart and lungs developed so they could work properly after hatching. The nervous system also became more advanced, allowing the young dinosaur to move while still inside the egg. Small movements may have helped prepare the muscles for life after birth. The shell protected the embryo from many outside dangers. It helped prevent injuries and reduce the loss of water from the egg. The shell also acted as a barrier against many harmful organisms that might have damaged the growing embryo. Even with this protection, eggs still faced many dangers. Floods, changing weather, hungry animals, disease, and damage from the environment could destroy eggs before they hatched. Only a portion of the eggs laid by a female may have successfully produced healthy young. Scientists believe that many large dinosaurs buried their eggs in soil, sand, or plant material. The warm ground may have helped keep the eggs at the proper temperature during development. Plant material that slowly broke down could also have produced heat. These natural sources of warmth may have helped the embryos grow until they were ready to hatch. Whether Giganotosaurus covered its eggs completely or left part of them exposed remains uncertain, because no complete nesting site belonging to this species has been discovered. Many scientists think the female probably selected a nesting area with care. She may have chosen ground that was high enough to avoid flooding while still being close to food and water. The nesting place may also have been located where the eggs could receive enough warmth without becoming too hot. A safe nesting area would have increased the chance that the eggs would survive until hatching. The number of eggs laid in one nesting event is unknown. Some dinosaurs laid only a few eggs, while others laid many. Large meat-eating dinosaurs may have laid enough eggs to increase the chance that at least some young survived. Nature is often difficult for newly hatched animals. Many young animals die before reaching adulthood because of hunger, disease, injury, harsh weather, or attacks from predators. Producing several eggs helped replace those that did not survive. As the embryo grew larger, the space inside the egg became smaller. Near the end of development, the young dinosaur filled much of the shell. Its body curled into a position that allowed it to fit inside the limited space. Before hatching, the embryo absorbed the remaining nutrients from the yolk. These nutrients helped provide energy during the first days after leaving the egg. When the time came to hatch, the young Giganotosaurus probably used a special temporary structure on its snout or jaw to break the shell. This structure, often called an egg tooth in many modern reptiles and birds, helped crack the shell without damaging the young animal. After making small openings, the hatchling slowly pushed its way out. The process may have taken several hours, because breaking through the shell required repeated effort. The newly hatched Giganotosaurus was very small when measured against the size of a full-grown adult. Even so, it already possessed many of the features needed for survival. Its eyes were open, its legs were able to support its body, and its jaws already contained small teeth. Although the teeth were much smaller than those of an adult, they were suitable for eating soft meat or other available food. Young hatchlings probably faced many dangers immediately after leaving the egg. Small meat-eating dinosaurs, snakes, crocodile relatives, mammals, and other animals may have hunted them. Even larger members of their own species could have been dangerous if food was limited or if they accidentally stepped on young animals. The first days of life were likely among the most difficult periods for a young Giganotosaurus. Scientists continue to study whether adult Giganotosaurus cared for their young after hatching. Direct evidence has not yet been found. Some dinosaurs appear to have protected nests or remained close to their young for a period of time. Other species may have left soon after laying eggs. Without clear fossil evidence, researchers cannot state with certainty how much parental care Giganotosaurus provided. If some level of parental care existed, it may have included protecting the nesting area from danger, guarding hatchlings for a short time, or leading them toward places where food could be found. Even limited protection during the earliest stage of life could have improved the survival of young animals. If little or no care occurred, hatchlings would have needed to depend on their own instincts almost immediately. Growth during the first years of life was probably very fast. Young animals needed to become larger quickly, because increased body size reduced the number of animals capable of attacking them. Rapid growth also improved their ability to travel longer distances, hunt larger prey, and compete for food. The bones of many large dinosaurs show signs of fast growth during youth through the study of growth rings inside fossil bones. Scientists can study the inside of fossil bones by preparing very thin slices and examining them under powerful microscopes. These studies reveal growth marks that formed during the dinosaur's life. Some of these marks show periods of rapid growth, while others indicate times when growth slowed. These patterns allow researchers to estimate the age of individual dinosaurs and understand how quickly they developed. During the early years, the bones of Giganotosaurus became thicker, longer, and stronger. New bone tissue formed continuously as the skeleton expanded. The muscles attached firmly to these growing bones, allowing greater strength and movement. As the skeleton developed, the joints also became stronger, making it possible for the animal to support increasing body weight. The skull also changed throughout growth. The jaws became longer and wider, creating space for larger teeth. The muscles that controlled the bite increased in size as attachment areas on the skull expanded. These changes allowed older individuals to handle larger prey than young animals could manage. The teeth of Giganotosaurus were replaced throughout its life. Like many reptiles, worn or broken teeth did not remain permanently. New teeth slowly developed beneath older ones. When an old tooth fell out, another tooth moved into its place. This continuous replacement allowed the dinosaur to maintain effective hunting ability even after frequent use of its teeth. Young Giganotosaurus probably hunted much smaller animals than adults. Small prey would have been easier to catch and less dangerous to attack. As body size increased, the range of possible prey also increased. Growing muscles, stronger jaws, sharper coordination, and longer legs allowed older animals to capture larger food sources. The brain also developed as the animal matured. Although the brain did not become extremely large, it continued to grow along with the skull. The senses became more useful as the young dinosaur gained experience. Sight, smell, hearing, and balance all played important roles in locating food and avoiding danger. Experience became an important part of development. Each successful hunt helped improve hunting skills. Each movement across different landscapes taught the young dinosaur how to travel safely through forests, open plains, river valleys, and other environments. Repeated practice allowed movements to become more effective as the animal matured. Food played a major role in growth. A young Giganotosaurus required large amounts of nutrients to build muscle, bone, skin, organs, and other body tissues. Meat supplied proteins and fats needed for continued development. Water was equally important because every part of the body depended on it to function properly. The digestive system processed food by breaking it into smaller substances that the body could use. Nutrients entered the bloodstream and were carried throughout the body. Cells used these nutrients to grow, repair damage, and produce energy. Waste materials were removed from the body through normal biological processes. Growth did not occur at exactly the same speed throughout life. Some periods were probably marked by especially rapid development when food was plentiful. Other periods may have shown slower growth because of limited food, illness, injuries, or environmental changes. Seasonal differences may also have influenced the availability of prey and fresh water, affecting overall growth patterns. The immune system also became important during growth. Young animals faced exposure to bacteria, parasites, fungi, and viruses throughout their lives. A healthy immune system helped protect the body from many diseases. Fossil evidence showing healed injuries suggests that at least some Giganotosaurus individuals survived wounds and recovered over time. As the young Giganotosaurus continued to grow, changes took place throughout its body. The muscles became thicker and stronger as more muscle fibers developed. These muscles allowed the animal to move with greater force and stability. The legs became capable of supporting increasing body weight, while the neck strengthened enough to carry a larger head. Every stage of growth required the body to remain balanced so that movement stayed effective as size increased. The arms also developed during this period. Although the arms were much smaller than the legs, they contained strong muscles and sharp claws. As the young dinosaur matured, these claws may have helped hold prey for short periods, assist in rising from the ground, or provide support during certain movements. The bones of the arms became stronger as more bone tissue formed inside them. The feet also changed with age. The toes lengthened, the joints became stronger, and the claws became harder through the production of keratin. Thick pads beneath the feet helped support the increasing body weight while walking across different kinds of ground. These pads also reduced stress on the bones and joints during movement. The skin continued to grow along with the rest of the body. As the animal became larger, new skin cells formed to cover the expanding body. Older skin cells naturally wore away and were replaced by new ones. Any injuries to the skin triggered healing processes that repaired damaged tissue. Small cuts and scratches could heal if they did not become infected. The blood circulation system also became more effective as the body increased in size. A larger body required the heart to pump blood over greater distances. Blood carried oxygen and nutrients to every tissue while removing waste products. Healthy circulation was necessary for growth, movement, healing, and normal body function. Breathing also changed as the animal matured. Larger lungs were able to take in more air with each breath. Oxygen entered the bloodstream and supported the activity of muscles and organs. During periods of hunting or fast movement, the body needed even more oxygen, causing breathing to become faster until activity slowed again. The senses likely became sharper through experience. The eyes continued to provide information about movement, distance, and the location of prey. The sense of smell remained valuable for detecting animals, finding carcasses, recognizing members of the same species, and identifying possible danger. Hearing also allowed the dinosaur to notice sounds made by other animals or changes in its surroundings. Learning probably played a greater role than simple physical growth. Young animals that survived each passing season gained experience from every successful hunt and every dangerous encounter. They learned where prey could often be found, where water was available, and which areas contained greater risks. This knowledge may have improved their chances of surviving into adulthood. As body size increased, food requirements also became greater. A larger animal burned more energy simply by moving its body from one place to another. Hunting, therefore, became an almost daily necessity. Missing too many opportunities to feed could weaken the animal, slow its growth, and reduce its ability to defend itself. Periods of injury may have interrupted normal growth. Fossil bones from large theropod dinosaurs sometimes show healed fractures, bite marks, and signs of infection. If Giganotosaurus suffered similar injuries, healing would have required energy and nutrients. During recovery, growth may have slowed while the body repaired damaged tissues. Broken bones could gradually heal if the injured dinosaur survived long enough. Bone cells produced new material that joined broken pieces together. The healed area often remained thicker than before, leaving evidence that could still be seen millions of years later after the bones became fossils. These healed injuries provide valuable information about the lives of ancient animals. Disease may also have affected individuals during different stages of life. Infections caused by bacteria or parasites could weaken the body and reduce the ability to hunt. Young animals were especially vulnerable because their bodies were still developing. Adults with severe illnesses may also have struggled to obtain enough food. Weather conditions influenced growth as well. Long dry periods may have reduced the number of available prey animals. Heavy rainfall could change river systems and affect where animals gathered. Seasonal changes in plant growth influenced plant-eating dinosaurs, which in turn affected the hunting opportunities available to large predators such as Giganotosaurus. As the years passed, the young dinosaur slowly approached full physical maturity. The rapid growth seen during early life gradually became slower. The bones continued becoming stronger, but they lengthened less than before. Growth eventually reached a stage where the animal was close to its full adult size. Scientists estimate the age of fossil dinosaurs by studying microscopic growth marks inside their bones. Each growth mark records a period during the animal's life. By counting these marks and studying their spacing, researchers can estimate how old an individual was when it died. Wide spacing often shows faster growth, while narrower spacing suggests slower development later in life. Once Giganotosaurus reached adulthood, much of its energy shifted from body growth toward maintaining normal body functions and reproduction. Adult individuals still replaced worn tissues and healed injuries, but they no longer increased greatly in overall size. Instead, they invested energy in finding food, defending territory if necessary, and producing offspring. reproduction began only after sexual maturity was reached. Scientists do not know the exact age at which Giganotosaurus became capable of reproducing, but large dinosaurs likely required several years of growth before their reproductive organs became fully developed. During the breeding season, males and females needed to locate one another. They may have recognized members of their own species through sounds, scent, body posture, or visual signals. Living reptiles and birds use many forms of communication during breeding, and dinosaurs may have used similar methods. Male Giganotosaurus may have competed for the opportunity to mate. Such competition could have involved displays of strength, loud calls, body movements, or physical contact. Fossils cannot fully reveal these behaviors because actions rarely become preserved. Scientists must therefore rely on evidence from related living animals and fossil injuries. Females likely became selective when choosing a mate because producing eggs required a large investment of energy. A healthy male with good physical condition may have increased the chance of producing healthy offspring. Natural selection often favors animals that are capable of surviving long enough to reproduce successfully. After mating, fertilization occurred inside the female's body. The developing eggs slowly formed as nutrients accumulated around each embryo. During this time, the female required a steady supply of food because producing eggs demanded large amounts of protein, calcium, and other important nutrients. Calcium was especially important because it helped build the hard shells surrounding the eggs. Strong shells protected the embryos while still allowing gases to pass through tiny openings. If calcium was limited, shell quality might have been affected, reducing the chances that the eggs would survive until hatching. As the eggs developed inside the female, the embryos began their earliest stages of life. Cell division started almost immediately after fertilization. A single fertilized cell divided again and again, producing many millions of cells that eventually formed every part of the developing body. Different groups of cells gradually became specialized. Some developed into muscles, others formed bones, skin, nerves, blood vessels, internal organs, or the brain. This organized pattern of development allowed the embryo to build a complete body before hatching. The female eventually laid the eggs in a prepared nesting area. She may have used her hind feet to scrape away loose soil before placing the eggs in position. After laying them, she may have covered them with soil, sand, plants, or other natural materials that helped maintain suitable temperatures during development.